What's up, math scholars? Mrs. Harp here. I hope you're having a happy week. It's Say Hello week, so say hello to a fellow scholar today at lunch, and maybe you guys can work on your math homework together. We are learning the last section of the chapter. Yay! It's all about graphs. So who's excited? Yeah! And don't forget to take a selfie with a math teacher and put it on Twitter with hashtag Bex and Cares, hashtag Math Scholar. I don't know what the prize is. All right, first things first, we're going to talk about slopes. Slopes can also be referred to as rates of change. So if you see the term rate of change, it just means slope. Now, would this particular graph have a constant rate of change throughout the entire graph, or would it change? It would be constant. It would always be positive, correct? What about this graph? Would it have a constant rate of change throughout? No. Yeah, this is an exponential growth curve. That was scholarly. But basically, the slope from here to here would be a positive slope, but it would be much less than the slope from here to here. So we'll be doing scenarios today where we find slopes at different intervals, and they will be changing if it's a curved line. What about this one? Would the slope remain constant throughout? No. The slope from like here to here would be much steeper than the slope from here to here, and these would all be negatives, and then by the time we got over to here, that would be positive, and that would be even steeper, and it would still be positive. All right, so it would change depending on where you're at. All right, let's read a little story. This is kind of fun. You get to read a story, and you get to draw a line that kind of would represent the plane in this one. A small plane is flying at a constant cruising altitude. So let's draw it. Flying, flying. It is caught in a storm. Air currents carry the plane up before pushing it down rapidly below its original altitude. The plane exits the storm and returns gradually up to its cruising altitude. So I think they wanted to do this so we could just have a chat about slope. Would we have any slope to this section here? What would be the slope of this section? 0. What would be the slope of this section? Positive. What would be the slope of this section? Negative. And then a slight positive slope until we get back to where we started. What else did they say? I think that's good. All right, so let's talk rate of change. It's got a formula. You should remember this from not yesterday, but last year, the year before. You've probably been doing slope formulas a few years now. I have a little song. Y minus y over x minus x equals slope. You don't necessarily have to do y2 minus y1 over x2 minus x1. You could reverse the orders. You just have to go in the same order both times. Slope. Y minus y over x minus x equals slope. What? Today easy? All right, we're back with our very first rate of change problem for the day. If I would graph this, do you know what shape it would make? It's an exponential growth curve, so it would kind of look like this. So it's probably not going to have the same rate of change over different intervals because it will be steeper at one point and not as steep at another point. When they say to find the average rate of change over a specific interval, these are both x values. So my advice today is to make them into a chart, an xy chart. Put both of these in for x. How could you find their corresponding y values? There's a few ideas. Huh? You could put them in one at a time in for x and calculate them, or you can just put this equation into Graph World and generate the table. So it's totally up to you. Let's go ahead. Do you want to do the table way? All right, let's just do the table way. Get your calculators pulled up. All right, so we're going to put in 2 caret x minus 2. Make your cursor large again, plus 1. If you want to, just for fun, see what the graph looks like, you can go ahead and click graph, but it's that exponential growth that I was talking about. And then table. Where my move go? Second. There we go. So at 2, we're at 2, and at 0, we're at 1.25. Now you didn't need table to do this. You could have put each number into the equation one at a time. So now we get to do our slope. So y2 minus y1, x2 minus x1. On the top, you'll have 0.75. On the bottom, you'll have 2. And your slope will be 0.375. So not all that steep at the beginning of the curve. Yeah?
If you're given like a unit in the question, should we include the
Oh, like inches or something? Yeah. Sure, but I couldn't see them doing a unit in this one. The slope formula itself is y2 minus y1 over x2 minus x1. So that's the formula we're using. Make sense? All right, we're going to use the same exact equation, but we're going to find the slope over a different interval. This time the interval we're doing is from 2 to 4. So I like to make my little chart just to organize my numbers. That 2 and that 4 are both x values, so just remember that. I know it almost looks like they're a coordinate, but the brackets mean that they're an interval of x values. So we already have the y value when x is 2. We just need the y value when x is 4. You can look at your table for that. What is it? I had changed my equation. 5? Okay. And now we're ready to do our formula. So that's a 4. y2 minus y1 over x2 minus x1. So 3 over 2 is 1.5. So it is getting steeper. It's that exponential growth curve. So I'll just show you what we're dealing with. Our curve looks like this. From here to here, the slope was not as steep as it is from here to here. That's why the slope is getting bigger. Okay? Any questions on that? Then the last topic we need to talk about today is even and odd functions. So I'll tell you what to write down from this slide. Basically, functions can be even, functions can be odd, or functions can be neither. And there's a couple ways you can check it out. The first and easiest way is just to graph them. A function will be even if it has some symmetry over the y-axis. So I would write down that even functions have symmetry over the y-axis, and odd functions have R180 symmetry, which just means if you would rotate them about the origin, they would look the same after being flipped upside down. Okay, so of course we definitely could just graph this right away and look at the symmetry, but I am going to show you the way you can use a little bit of algebra to figure out if they're even, odd, or neither. So what you can do is you can find f of negative x, and that is something we have done this year. We've plopped a negative x in every single place. And if you plop a negative x in every single place, you'd go ahead and simplify it down. If what you're left with is exactly what you started with, then it's even. If what you're left with is the opposite of what you started with, then it's odd. And if it's neither, then it's neither. So I'll just show you. Negative x to the third power would be a negative. And then a negative 7 times a negative x would be a positive. And this is not the same exact thing I started with, but it is opposite of what I started with. See how this positive turned negative and this negative turned positive? Since these are the opposite of each other, this is an odd function. Well, we're going to go ahead and graph it just to see that R180 symmetry and to show you that works, okay? So go ahead and plop that in your graphing calculator and see what the picture looks like. I'll do it in my handheld calculator here. X to the third minus 7x. Graph it. I'll do a quick sketch. It kind of comes up, comes back down, and goes up. It's kind of like a snake. But that is what R180 looks like, because it could rotate around that origin 180 degrees and still look exactly the same. Yeah?
Does something be not just or not? How could it be neither?
How could it be neither? We'll see one like that. Do you want me to go to a neither next? Okay. The next one is neither. I'll show you what the picture looks like. It's like the picture ends up being a hyperbola that's not quite centered at 0, 0. So let's just graph it first. When you go to put this into your y equals button, put that denominator in parentheses to keep it grouped. So 6 divided by parentheses x plus 1. When I graph it, it kind of looks like a hyperbola. But the problem is the center of the hyperbola kind of looks like it would be about here. So that's not going to be an R180 symmetry, because R180 symmetries rotate around the origin. Does that make sense? It's kind of off center of it. I'll show you mathematically what happens as well. So I will plop a negative in for my x. So it doesn't give me exactly the same thing, nor does it give me opposite of what I started with. To be opposite, this would have needed to turn negative, and this would have needed to turn negative as well. Okay. This is a typical neither. All right, we have one more to look at, and then I have to show you where a button is in the calculator. Okay. So if I forget to show you a button, remind me. I'm going to show you where the absolute value button is. All right, so this last one we're going to do. Do you want to graph it first or plop our negative x in first?
Plop our negative x.
All right, I like that idea. So I'm going to plop a negative x everywhere I see an x. And I'm going to simplify to see if I get the same thing back at me or if I get the opposite thing back at me. Check that right. Okay. A negative to the 6th power would turn positive, but I have this negative out front, so it will look like that. This negative will turn positive, so it will look like this. This negative will turn positive. Do you remember doing this earlier in the year? Yeah. And then earlier in the year we counted sign changes at this point. But today we're just going to say to ourselves, am I left with the same exact thing that I started with? Yeah, awesome. And that means it's even. And we can graph it, yeah. Somebody in my last class that graphed it told me she had to zoom in a bit, so let's go ahead and try it. Negative x to the 6th plus 3x to the 4th. She actually zoomed in on it really close and told me it looked like a cat. So that was interesting. That made my day really happy. Yeah, I didn't have to zoom in at all to see the cat. It's right here. It kind of comes up like a little ear. It comes down, it kind of loops around, and it comes up again. It's not quite that pointy. That's just a bad drawing. But yeah, so it is even, because it would have that line of symmetry coming straight down through the y-axis. All right, so the very last thing I need to show you is where the absolute value button is on the calculator. So there's a homework problem tonight where you have to graph the absolute value of something. So we're going to try to graph the absolute value of x, okay? So to get the absolute value button, you hit math. Then you hit right arrow because you need to get into the number menu. And then you hit number 1. So just for fun, let's see what the graph of the absolute value of x looks like. Anybody know? Have you done it before? It makes a V. Awesome. You've done it before. What class did you do it in? Oh, you did it. Yeah, it makes a V. So would that be even or odd? Even. It would have that symmetry over the y-axis. And here's a question. Is it a function? Do you remember the test if things are functions? You do the vertical line test, and it is. Yep, the absolute value function is definitely a function. Okay, we're done. I'm going to pass out your worksheet. It's a half a sheet of paper, I believe. And stop my video. Hopefully you had a good time watching today, scholars.